So we're talking about waves, both standing waves and moving waves. Standing waves are the hydraulic jumps we were talking about. And all these waves are characterized by the dimensionless Froude number. Also, we can talk about some applications of hydraulic jumps. So these aren't just naturally occurring things, but they can actually be used. Okay, so a few applications. Let's say that we have some fast-moving water down a canal and we're afraid that downstream it's going to hurt some object it runs into, pylon or something like that. So we can use a hydraulic jump to dissipate energy. On purpose, and so that the water doesn't do damage downstream, because these hydraulic jumps are actually going to have head losses, which we're going to calculate really soon. They can also be used for mixing. So as you saw before, there's a lot of swirling that goes on with these, so such as in sewage and water treatment, you might want mixing. And finally, we could actually take a look at a hydraulic jump and from that figure out what the flow rate is. So measuring flow rate is an application of hydraulic jumps. Okay, and again, like I said before, these things also apply to supersonic flight. And rocket exhaust. Shock waves. All right, so what we're going to do now is derive our equations. There's a number of equations that you're going to be able to use for waves, for hydraulic jumps and moving waves. And they're really the same equations. It's all just based on your frame of reference. So if you are looking, say, at a moving wave, you want your frame of reference to be on that wave. So pretend you're a surfer on that wave. And if you are the surfer, then you are standing still, or it feels like you are standing still, and the water in front of you is coming towards you, and the water behind you is going away from you, right? So from your frame of reference, water, it's just like the Halo guy, Chief, Master Chief, right? So the water is coming towards you and moving away from you behind. Okay, so basically the surfer, you can treat them as just standing still, water coming towards them. So just like a standing wave, all works the same. So what we're going to do is apply all three of our conservation equations: conservation of mass, conservation of linear momentum, and conservation of energy to this problem to come up with these equations. And then we're going to be able to use those equations. They'll be available to you on your equation sheet. So starting with conservation of mass. So the problem that we have here is we've got incoming water level, and then we've got our wave. All right, so here at 1 we have a depth, call it y1, and here at 2 we have a different depth. After the wave it's deeper, call that y2. All right, and here we're going to have a v1 and here a v2. Okay, this is our water surface. It's really not going uphill. I just can't seem to draw. It should be straight. And let's say that this has a width b into the page. All right. So here is our wave. Okay. So first thing we're doing is conservation of mass, which we're looking here at our inlet. This is 1, here is 2. So if we have steady state, assume steady state, then m dot 1 equals m dot 2. All right, and our m dot is rho v1 a1 equals rho V2A2. All right, well, we can do some substitutions. First of all, it's incompressible, so we can cancel the rows. And then we can substitute in our A. So if this is, say, a rectangular channel into the page, then we got V1, and our A is just going to be B times Y1. And if we look at V2, the area right there is now B times Y2. Well, those B's are going to cancel. All right. So all we have to do then is rearrange a little, and we can see that V2 is going to be V1 times Y1 over Y2. All right, so there's one of our equations. Conservation of mass gives us that equation. You'll find that equation on your equation sheet. So let's go on to conservation of momentum. All right, so first thing we need to do is draw a picture again. So we have our standing wave or a regular wave. And what we're going to do is we're going to do conservation of momentum for a little control volume that just crosses this wave. And unlike our usual procedure for conservation of momentum, we are going to put this all inside the flow. Okay, typically we'd cut right outside to outside the flow. All right. And when we do this, just remember this width here is infinitely small, really, across that wave, or it's very, very small. So the reason we didn't ever do this before is because we wanted to avoid the shear force. Well, since we're making this very, very small here, we're going to assume that shear force is negligible anyways, and so it's okay to do this. So the conservation of momentum equation then, we're going to call this 1, and this section 2. So this is our inlet, this is our exit, this is our depth here, this is our depth here. And our conservation of momentum equation, remember that was the one with the forces. So sum the forces due to pressure plus sum of the forces due to gravity plus sum of the forces due to shear plus sum of the forces due to other things, cutting through solids, is going to equal to, we only have one inlet and one exit here, and m dot is the same, so m dot v2 minus v1. All right. So let's right off the bat, like I said, we're going to neglect shear. Doesn't mean all our losses are gone, because we're going to have swirls and stuff that cause losses, but it's going to mean that the frictional losses right down here are just small compared to any other losses. So let's also write this in the x direction. So that's our main velocity direction. And if we do the x direction, we still have forces due to pressure. So let's say sum of the Fx pressure. Okay, no more gravity. Oops, I should have crossed out this other because we're not cutting through any solids. That is going to equal m dot times, well, our v2 vector in the x direction, well, that's just v2 minus v1. So if we call this v1 and this v2, then there we have it. All right, so one more little assumption. Since we are neglecting shear, we're neglecting friction along the bottom, what happens is our pressure then acts a lot like a static situation. So we don't have basically the slip condition or the no slip condition causing changes in velocity. It's all constant velocity. So if that's the case, then we can write our pressure just like we did in statics. So it's going to start at 0 gauge at the top, and it is just going to increase due to depth. And if you remember, whenever you drew the pressure forces, they always had to go from outside your control volume into your control volume, and that's going to help us get our signs right. So also from statics, if you remember, F pressure, was just equal to P at the center of gravity times A, which was equal to rho G HCG, that's our pressure at center of gravity, times our area. Okay, so we're going to have one of those at 1 and one of those at 2. And so if we rewrite the x direction, we're going to say, well, FP1 minus FP2 is equal to m dot V2 minus V1. Okay, so we're going to be able to plug in for FP1 and FP2 right here. We also need an m dot. M dot, if you remember the equation for m dot, well, that's just rho VA. All right, and we could put rho V1A1 or rho V2A2. Let's go with 1. All right. And our area that we're talking about in both of these are our cross-sectional areas. Okay, so our cross-sectional area here is Y1, the height, times B into the page. So B equals width into page. It's supposed to be a B. B. All right. So let's do all our substitutions here. Our FP1 is going to be rho G HCG1. Well, HCG, remember that's just halfway down, so that's Y1 over 2. And then our area, Y1 times B, minus at 2, similarly, rho G Y2 over 2 times Y2B. And then that equals rho V1, well, our A1 is Y1B times V2 minus V1. All our rows cancel, all our B's cancel, and what we're left with then is GY1 squared over 2 minus GY2 squared over 2 equals V1Y1 times V2 minus V1. All right. What we can do then is rearrange this, and the other thing we can do is use our conservation of mass. So we already know that V2 is equal to V1 times Y1 over Y2 from a conservation of mass. It's a cons of mass. All right, so I can substitute that in for V2. And if I just rearrange, then all I have in my equation are y's and V1. All right, so I'm going to just say algebra. And what you're going to get is an equation that is in our equation sheet. And that is V1 squared is equal to 1/2 GY2 times Y2 over Y1 plus 1. All right, a little algebra there. You got an equation on your equation sheet. So, bottom line is when you're doing a problem with open channel flow across a hydraulic jumper or wave, you can jump right to this equation. You know that that equation came from conservation of linear momentum, but it's already going to be there on your equation sheet for you. The other thing to notice is if I plug this back in, instead make this in terms of Y1, I'm going to have my Froude number in here. If you remember Froude number at 1 is V1 over the square root of GY1. All right, so again, a little bit more rearranging. And I can get another equation that's on our equation sheet. So that would give us, so this one gives us V1 in terms of our heights, which are probably pretty easy to measure. But but we can also get our heights in terms of our Froude number. So 2y2 over y1 is equal to minus 1 plus 1 plus 8 Froude number at 1 squared to the 1/2 power. Okay, and that just comes from solving the quadratic formula. You can almost see it in there. Minus b plus or minus, this would be the plus, the square root of b minus 4ac all over 2. All right, so that's what you get, another equation on your equation sheet in terms of Freud. And if you're really interested in doing the algebra, by all means do it. All right. So let's think about these equations in terms of an infinitely small wave. And if it's an infinitely small wave, what that means is y1 and y2 are about the same, which means the ratio y2 over y1 is equal to 1, right? Approximately equal to 1. All right, so we could plug in 1s here for our ratios and rearrange. And what we're going to get is v1 squared is about equal to gy1. And if you remember, for a small slow wave, that was equal to our c naught, we called it, c naught squared, where c naught equals the speed of an infinitely small wave. Okay, and in aerodynamics, that's analogous to the speed of sound in a fluid, A, all right, which goes into the Mach number. So this is our denominator of our Froude number, very similar to the denominator of our Mach number. Let me just write that that is for aerodynamics. All right, so that is our conservation of momentum and a couple of equations that it gives us. We had from above, conservation of mass gave us this, an equation for V2 in terms of V1 and our y's. So let's finally do conservation of energy. So the losses, we're ignoring frictional losses, but there are still losses. They're kind of like minor losses. We are going to call them HF in our equation, but they're really kind of like minor losses. So what we're going to do is we're going to do conservation of energy, and in general, when we're doing open channel flow, we're going to do it along a streamline, and that streamline is going to be the free surface. Okay, so the top surface, and the good thing about using that is that P1 equals P2 equals 0. Okay, so we're not going to have to worry about P's. That's, of course, gauge pressure. Okay, so let's write our energy equation. That was P1 over rho g plus V1 squared over 2g plus, this time, since we are using the free surfaces, our streamline, our Z1, we can make that Y1. And then our P2 over rho g plus V2 squared over 2g plus Y2, and then plus our HF plus HM plus HS. Well, we aren't going to have any pumps or turbines in there. We're going to call these losses frictional head losses, even though they're really more like minor losses. We just said we could cancel these out. All right, so what we also know, we can plug in conservation of mass and what we got from conservation of momentum. And what we're going to end up with is, again, algebra. HF equals Y 2 minus y1 quantity cubed over 4 y1 y2. All right, so with that, we can figure out what are our losses, head losses, due to just going across that wave, having that hydraulic jump. All right, so we did all three of those conservation equations. Now let's apply it to an example. And most of these problems are going to be, okay, if you can visualize this and do a good picture, it's going to be a matter of plugging into these equations and manipulating these equations, sometimes having to do some substitutions and so forth. But it's not too bad. So let's say we've got a hydraulic jump. Same old picture. So that just means a standing wave again. We got a y1 and we got a y2. Happens to be 40 centimeters to 140 centimeters. And we are going to try to find V1, V2, critical depth, and percent of dissipation. All right, so starting with A, we're going to find V1. Well, V1, this is V1 here, and this is your V2. We just found an equation in terms of y1 and y2, and we know both y1 and y2 for V1. So let's just jump to that equation. So if I look on my equation sheet, I see an equation, V1 squared equals 1/2 g y2 times y2 over y1 plus 1. All right, no problem. I can just plug into this, and I'm going to just say plug in, and you can try it on your own. But you know G is, this is metric, 9.81 meters per second squared, Y2, 1.4 meters, and so forth. And you're going to end up with V is equal to, this is V1, is equal to 5.56 meters per second. So far this has just been plug and chug. Nothing wrong with that. All right, so let's go on to V2. Now that we know V1, we know Y2 and Y1. Aha, conservation of mass, another equation that's right there on your equation sheet. V2 is equal to V1 Y1 over Y2. Again, plug in. Plug in that 5.56, plug in your 0.4 meters and your 1.4 meters, and you're going to get 1.59 meters per second. Easy. All right, this is where it gets a little bit more confusing, where you got to know what you're doing a little bit more. All right, so the next thing we want to find is the critical. Find the critical depth, YC, right? Or was it critical velocity? Critical depth, which is called YC. So what you have to do is you have to remember, well, the critical depth happens when Froude number is equal to 1. And let's just put C. Froude number critical equals 1. Kind of like Mach number equals 1. And the Froude number would be V critical over the square root of GY critical. All right. So this is all well and good, but problem is we don't have V critical, okay? Or else we could just solve for YC, just plug and chug like we did before. So we need one more equation because we have two unknowns in here. Well, the easiest equation we have is conservation of mass. And remember, conservation of mass is going to work on pretty much any set of velocities and heights, as long as you're careful. One inlet and one exit. So we can say our conservation of mass, well, Q1 equals QC, okay? That's canceling out the rows already in the m dots. M dot 1 equals m dot C, okay? So cancel out the rows, you get Q1 equals QC. So V1 A1, and A1 is Y1B, equals V critical, Y critical, times B. B's cancel. And this is just our conservation of mass equation, we can really apply it to any two heights and velocities. It doesn't have to be 1 and 2. But what we get is V critical then is equal to V1 Y1 over Y critical. And this can then be plugged in up here. All right. And when we do that, now we'll have an equation with just YC in it. So 1 is equal to V1Y1 over Y critical square root of GY critical. And believe it or not, I can solve this using regular algebra. You could do your solver, but you don't need to. That's equal to V1Y1 over square root of G Y critical to the 3/2. Okay, and just rearranging, I can solve that. Y critical is equal to then .80 meters, 80 centimeters. It should always end up between Y1 and Y2, or else there wouldn't have been a hydraulic jump, because it's going to go from supercritical to subcritical as it crossed that hydraulic jump, which is like a shock wave. Okay, so critical has to be between 1 and 2, or there wouldn't have been a hydraulic jump. Also, just on your equation sheet for future reference, if you're given Q, there is another equation. YC equals Q squared over B squared G to the 1/3. We didn't really want to use this equation because we don't have a B, but had we been given a Q and a B, this one would have been a good one to use. And it came from exactly the process we did here, but just in terms of Q and B. All right, part D then was find the percent of dissipation. Okay, what they're talking about, percent of dissipation, let me look back up exact wording, percentage of dissipation. So dissipation they're talking about is energy dissipation across that wave. Okay, and what we're going to do is leave it in terms of head form, so our energy head, but dissipation means losses. Okay, so we're going to have losses, and we had an equation from our energy equation, HF, and this is straight off your equation sheet again, Y2 minus Y1 cubed over 4Y1 Y2. All right, and again, I can just plug in, and I'm going to get 0.446 meters. All right, so those are our head losses, but that is not exactly what it was asking for. It wanted a percent of dissipation. A percent of what? Well, that what would be the original energy head that we had before we got to the hydraulic jump. So E1 is going to be, well, if we're talking again, we're always going to be using the top for our energy equation, the free surface for our energy equation. So P is going to be 0, so we can skip the P term. It'll be just our kinetic energy term, V1 squared over 2G plus our elevation, Y1. So that's the energy we're starting with, and we know all these values, so that's just going to be our 5.56 meters per second squared over 2 times 9.81 meters per second squared plus our Y1, which was 0.4 meters. All right, so our E1 comes out to be 1.976 meters. That's our energy in head form that we came in with, and then we hit the wave and we lost this much. All right, so the percent dissipation, or the percent loss that we have, is going to equal 0.446 meters over our 1.976 meters, which is about 23%. All right, so that's it.